the Sustainability Management Master's Program, you're answering one simple question. Do you care about your future generation? If you care about your kids, their grandkids, then you care about sustainability. And a sustainability manager is someone who has the tools to make people understand how they can contribute towards developing a sustainable world. We have both part-time and full-time students. Our curriculum is 30 hours. Instead of thesis, we have a research project course and a seminar course which provides them with the kind of research background they will need to be successful in their job. But at the same time, sustainability is not always everything about environment. It also relates to the business. They will take a sustainable business strategies course. They will take a project management course. Most of these courses are going to be taught by industry people, the people who are doing sustainability on a daily basis as a part of their job. Any organization that has a large number of employees and has a physical infrastructure, they will have to have a sustainability office. If you have the passion to develop and maintain a sustainable world, come to us and we will help you shape your passion into a career which will create an impact.
Not waste much time, so straightforward, I'll go to my next slide. So I am, as introduced by Dr. Deeps, I am Debasis. I am from India, currently doing my postdoctoral research at North Dakota State University. So today I will tell briefly about the mitigation of arsenic from soil and water. So I will talk under these heads, mainly sources of arsenic and affected areas. Then the major concern is the toxicity symptoms in humans. Then I will discuss briefly about the risk assessment. Then little bit I will touch the model, different model for prediction of arsenic transfer. Then one case study, what I did in Malda district, the mostly affected district in West Bengal, then mitigation options. So I don't know the type of audience here. Still, I will start from the basic chemistry with the definition of metal and metalloid. So if we look into the periodic table, then what is metal? Metal is actually any element which is having the specific gravity more than 5 or the atomic number more than 20 is called as metal. And the non-metal is poor conductor of heat and electricity. And what is metalloid? Metalloid is in between metal and non-metal. So our today's discussion is on arsenic, and arsenic is considered or termed as metalloid. So arsenic is a metalloid, and there are several hypotheses for this arsenic poisoning in groundwater. I will not tell about this hypothesis, this arsenopyrite oxidation and ferric oxyhydroxide reduction. These two theories are very common for explaining the arsenic poisoning in groundwater. Now, what is the need of the hour? So as we see that the major arsenic problem is through geogenic sources, other activities. We are also responsible for arsenic poisoning in the environment, mainly through application of sewage water, industrial waste, municipal solid waste, then fertilizer and pesticide application. However, it is considered that the application of arsenic enriched or arsenic contaminated irrigation water to soil is the major culprit or main culprit for arsenic poisoning in agricultural land. So remember this thing, application of irrigation water that is enriched with arsenic. So my main concern is the transfer of this arsenic from soil to human food chain via rice crop. You know, rice is a great accumulator for arsenic, and among all agricultural crops, Among all agricultural crops, rice is considered to be the highest accumulator of arsenic. So, and another thing is, first thing is food chain contamination. This is a major issue. Earlier, we ignored this thing so much, but now people, they are so much concerned about the food chain contamination of arsenic. So the problem is with, we don't have any safe limit of arsenic in soil. What we have, the arsenic limit in drinking water. We have the limit in drinking water. We have the limit in irrigation water, but we don't have any limit in soil. What we have, that is total arsenic limit. But the requirement is available arsenic. What is the limit of available arsenic in soil? That is important, and that should be linked with the human health. So I will show you what research actually we carried out to set the safe limit of available arsenic in soil in relation to human health. That is important. So what I said, the food chain contamination with arsenic, how it happens. I will show you the sources, the affected areas or affected regions of arsenic. But the thing is, what I want to convey here, that the food chain contamination with the application of irrigation water in rice crop, mostly in Asian countries, rice is a staple food. So the consumption rate is so high. So application of this arsenic loaded irrigation water ultimately leads to the uptake of that arsenic to the rice grain, and rice grain ultimately we consume on daily basis. So this is the food chain contamination is taking place. Now coming to the arsenic affected countries of the world, now as on today, over 200 million people in more than 50 countries are probably affected by arsenic poisoning through drinking water. And mostly it is in South Asian and South American regions are mostly affected. So if we look into the scenario in US, then the states showing the increasing arsenic exposure through drinking water in different states in US. So this is the part of the Indo-Gangetic plain. This Indo-Gangetic plain is mostly affected with the arsenic problem, mainly covering the 6 states. So some work actually I did, some survey which I told in the introduction slide. So one, this state of India, that is West Bengal, it is mostly affected state with arsenic poisoning. So what we did, some work in West Bengal state of India, mainly in Nadia district and Malda district of West Bengal, India. Now you can see this photograph actually I took in 2016 while we were working with close association with medical specialists, doctors in our team. So we have identified some manifestation of chronic arsenic toxicity. So you can see the problem with the chronic arsenic toxicity is mainly it is the skin manifestation, which is called pigmentation and keratosis. So these cases actually we have identified in Malda district along with DNGM Research Foundation, Kolkata. So this is another skin manifestation of chronic arsenic toxicity. So after long-term exposure of arsenic, the manifestation will be in terms of either pigmentation or keratosis. So it looks like this. The previous slide, yeah. So the body tongue is just looks like this, and the keratosis is it may be appear in your hand or in your leg like this. The appearance would be like this. So the long-term chronic chronic poisoning or long-term chronic arsenic toxicity looks like this. So apart from pigmentation and keratosis, other manifestation of chronic arsenic toxicity are systematic manifestations, respiratory disease, gastrointestinal disease, liver disease, cardiovascular disease, nervous system, problem in nervous system, then hematological effects, pregnancy outcome, or arsenicosis, and ultimately the cancer. The impact of the chronic arsenic toxicity result ultimately will leads to the cancer. We also identified cancer patients in Malda district. I will show you the data. So this is the problem. So we need to go for appraisal. Without appraisal, we can't control or we can't manage the things. Problems we have, so many problems we have. Like in our health, we have sugar problem, we have say other disease problems. So for that, we went to doctors for the appraisal, for the assessment, for the remedy, for the things actually we have to do. So similarly for arsenic problem in drinking water as well as arsenic problem in soil, we should go for the appraisal. So the first step is the risk assessment. So here I am not going to give you a details account of risk assessment, how the concept actually arises, and the concept is very old. US EPA, they actually, United States Environmental Protection Agency, they time to time revise this risk assessment protocol. They have integrated a risk assessment system, IRIS in short. So US EPA, they actually time to time revise the system of this risk assessment. So one by one, I will tell you. So the first is your maximum allowable limits of arsenic in soils. So we have limit, what I told, we have the total arsenic limit in soil, but not available arsenic in soils. So total arsenic limit we have, like we are following the Great Britain concept. So total arsenic limit is 10 to 20 ppm, that is milligram per kg. If a soil is having more than 20 milligram per kg of arsenic, then the soil will be termed as arsenic polluted or arsenic contaminated. The soil is polluted with arsenic if it is more than 20 ppm. Similarly, we can assess our drinking water. We know that drinking water, it is also a major source. So apart from soil, the drinking water, we have the limit for drinking water. World Health Organization, they have prescribed the limit for 10 ppb. If your drinking water is having more than 10 ppb of arsenic, then the water is unfit for consumption. So similarly in rice grain we have the limit, but nowadays we are following the limit of 0.2 ppm of arsenic, that is 200 ppb. 200 microgram per kg of arsenic in rice grain is the limit. If the rice grain is having more than 200 ppb of arsenic, then the rice grain is unfit for consumption. So these four types, what the appraisal, maybe the category I have shown. So other than appraisal, like your hazard quotient, this concept actually given by United States Environmental Protection Agency, hazard quotient calculation. Hazard quotient we can calculate for both for drinking water as well as for rice grain. So hazard quotient is actually considering the additional parameters like our body weight as well as the body weight, as well as the obviously the metalloid content, that is arsenic content in grain. That parameters we are considering. Then daily intake, that is important. How much rice we are taking, how much drinking water we are consuming. So that is important factor. So hazard quotient, the advantage of calculating hazard quotient is it actually calculating both your body weight as well as the amount of material we are taking. So the The convention is if the value of hazard quotient is more than 1, then the particular food material is unsafe for human consumption. Similarly, for drinking water, we can calculate hazard quotient. Okay, so for that we need to estimate the arsenic content in our food materials. You all know arsenic we can measure with the help of uh, instrument like ICP-MS or atomic absorption spectrophotometer connected to hydride generator. So these two instrument is basically used for arsenic measurement. So this is the last approach for arsenic appraisal. This is our contribution, what our research team actually did in past few years. We use the integrated approach. I will show you how we actually develop the safe limit of available arsenic, but I will not discuss in details, I know. So this is the model. I will not I will not tell about much more details about this model. Only the thing is solubility and free ion activity model actually we used for all experiments. One message I want to convey here that we have developed a software. With this software actually we can tell the safe limit of available arsenic in soil considering human health as well as soil properties like pH, organic carbon, also an extractable arsenic. So these parameters actually we are giving as input in our software to get the available arsenic limit. That is important. Available arsenic. Why it is important? Because if you don't know the available arsenic limit in soil, then you can't blindly grow your agricultural crops until and unless you know that your soil is safe, then you can grow your agricultural crops. Okay, so this is the case study what we did in Malda district of West Bengal, India, where the arsenic problem is great. So these our objectives. Yeah, so this what I told that we did this work in association with the medical team from DNGM Research Foundation. So the doctors they actually identified the disease burden in that area due to prolonged arsenic consumption through drinking water as well as rice grain. So if you remember, I told the main problem is with the main disease of arsenic poisoning is pigmentation and keratosis. So the criteria for classifying this disease is mild, moderate, or severe based on the identifications. Okay, so based on the disease burden, doctors actually they actually identified the scores, like your mild, moderate, severe. I will show you the data. Yeah, so this is the patients we identified in that area, the chronic arsenic problem in terms of pigmentation, and this is keratosis, severe keratosis. Yeah, this is the data of our survey. You can see this table is showing the demographic data, because you know the arsenic problem it is actually closely linked with our social status. So what we try to find out their social status in terms of their education, their income, and yeah, this is the main data where we identified the pigmentation and keratosis. So we recruited 182 people in that area, and then we put the pigmentation and keratosis disease data. Along with this pigmentation and keratosis in that area, what we identified the disease like your other disease like cough, then dysphonia, then weakness, diarrhea, limb pain, tinging, and cancer. One patients, what we identified cancer patients in that area. So this is important that the arsenic exposure to drinking water and raw rice grain, what we collected in that area, both from patient's house as well as from non-patient's house, and what we found there is a close correlation between the patient's house drinking water and rice grain with their disease burden. So with increasing the arsenic content in their rice grain, what we collected from the patient's house is actually showing the higher disease burden as compared to the control house. Okay, so you can see that area having the mean arsenic content, it is more than the safe limit. 364 ppb, it is more than the permissible limit, that is 200 ppb is considered as safe. Sorry, for drinking water it is 364 ppb, but the safe limit is, if you remember, it is 10 ppb only. So the area is greatly affected. Similarly, for raw rice grain, if you see the mean level, though it is low, though it is below the safe level, but the maximum, if you see, in most of the cases, the arsenic content in that area exceed the safe level, that is 200 ppb. So these are our salient findings from that area. I want to mention here that the uh, drinking water and rice, drinking water, this is well identified source, but the rice is also identified as a major exposure route in that study area, and in most of the cases it exceeds the permissible limit for safe drinking water, what I shown you in my data. So this is the area where we carried out this research work. So apart from that, that is actually kind of social dimension, social part. The soil science part, actually we also collected our soil samples in this area, from this area, and we analyzed for different parameters like pH, carbon, extractable arsenic, then total arsenic. Then we also collected these soil samples from both patient's house, patient's field, as well as the controls field. Okay, so this is the summary of that area. This apart from rice, we also analyzed wheat crop and maize crop. And the good thing is that, as I said, rice is a great accumulator of arsenic. So wheat, actually it accumulates much less arsenic than maize crop. If you see the mean arsenic content, it is less in wheat crop, 83.8 ppb, and in maize it is 82 ppb. So it is a good message that if we grow, or in US the main crop is not rice, where wheat and maize, it is actually mainly grown, so the accumulation of arsenic is much less in these crops. Okay, so these are salient findings. What I wanted to convey here, that the arsenic content in cereal grains followed the order: rice is the highest accumulator, followed by wheat, and then maize. So this is actually the model, what we fit the model. So I am not going to describe this thing. The R square value what we got is very high. Yeah, this is important. The hazard quotient calculation for in this study area, the drinking water and rice, you can see what I told earlier, the hazard quotient limit is 1. If the HQ value is more than 1, then the material is unsafe. So in the study area, you can see for drinking water it is 12, it is too high. So the hazard quotient value exceeds the safe limit of 1 in case of drinking water, as well as in case of rice crop. So this is the safe limit. We actually, what I told, that we have developed a software. So with that software, we have prescribed this safe limit in Malda district of West Bengal, India. In that soil, we have prescribed the safe limit of available arsenic, like 0.43 ppm, 0.43 ppm. The condition is like pH and organic carbon should be 7.5 and 0.5%. So I'm not going to give you the details about this. The thing, actually we have published, we could able to publish in Ecotoxicology and Environmental Safety Journal. So the main message is that the integrated approach by physicians and soil scientists was adapted to assess the arsenic hazard. So our main message to all of you that nobody can, that single means entity or like only solely soil scientists can't solve the problem. So we should do our research together, the integrated approach, like if we can collaborate with physicians, if we can collaborate with plant scientists, then the problem can be solved. This is the main message. Now coming to our last part, the mitigation strategy for arsenic removal from water and soil. What we did for last few years. So I'll show you. So this is under the Fulbright program. I forgot to mention that the Fulbright program, under Fulbright program, I am working with the development of some novel materials for remediation of arsenic in rice crop. So here I have started to synthesis some nano zero valent iron. You know, this nano zero valent iron concept is very old. So we are trying to refining the material. We are trying to develop the things so that we can effectively use this material for arsenic removal in drinking water as well as rice crop. So this is the initial data, like we have standardized the dose for different materials. We have synthesized bare or the conventional nano zero valent iron, then sulfonated nano zero valent iron. So this is our main product. We are trying to maximize the arsenic removal from aqueous system. And another one we have tried with bentonite based sulfonated nano zero valent iron. So bentonite, you know, clay is very abundant in our say in the environment. So we are trying to preparing some materials that actually that is bentonite supported sulfonated nano zero valent iron. So what we found that 200 milligram per liter, the 200 milligram per liter of sulfonated nano zero valent iron. So this material is effective for 100% removal of your arsenic. 200 milligram per liter, 200 milligram per liter is sufficient for 100% arsenic removal. So the performance is much higher for sulfonated nano zero valent iron as compared to the normal or the bare nano zero valent iron. What we found that the material is effective throughout the pH medium, like your acidic to alkaline. However, the highest we can see from the bar that the effective pH is from 4 to 10. The material is working under this pH range. So this is another work what we carried out. The conventional rice varieties we actually collected from the Nadia district, another district which is affected, Nadia district of West Bengal, India. That is also worstly affected district. So from there actually the local rice varieties we collected that time and we grown in our greenhouse experiment. What we used, sodium metasilicate. Sodium metasilicate is also a it can also be used as a remedial say treatment, sodium metasilicate. So what we found that the hazard quotient value after application of different doses sodium metasilicate, like control, then 250, then 500 milligram per kg of sodium metasilicate dose actually we used for growing these 4 rice varieties, 4 conventional rice varieties. So where we found that the hazard quotient value, it is actually it goes below 0.5 when we apply the highest dose, that is 500 milligram per kg. Another approach for mitigation of arsenic, we tried alternate wet and drying along with phosphate and vermicompost application. You know, these are the different amendments what we can use for arsenic removal from soil. So what we got, that the integrated use of this alternate wet and drying and phosphate and vermicompost application effectively reduce the arsenic transfer in rice grain. You know, this rice crop, you all know that rice crop either we can grow under continuous submergence or under alternate wet and drying condition. So what we recommend, the rice, it should, if we can grow under alternate wet and drying condition, then we can effectively remove the arsenic transfer from soil to rice crop. So I'm not going to give you the details account what we got the different R square value from our model. If you remember the model, solubility, free and activity model. So yeah, this is important because this is a field study, you know, the field agricultural field where actually rice or your wheat and maize we grow. But this experiment we did in wheat and maize crop under field condition in Bihar state. If you remember, I said 6 states are mostly affected in India. So in wheat and maize field, we tried with different amendments, and what we found that sugarcane bagasse and paddy husk, these two amendment materials is very effective in reducing the arsenic content in soil as well as in crop. So this is the last slide. This is the future direction of research. What we found, we should do some research like developing standards, development of standards in terms of safe, marginal and lethal levels of arsenic in human is very important. Development of standards, this is important. Then you know, arsenic, it may be it has actually so many species are there. So speciation studies, though some research is going on around the world, in and around the world, but the speciation, accurate speciation is very important. Then your rationalization of safe value of HQ for routine risk assessment is required, because US EPA, they are recommending the hazard quotient value, it should be 1, but we in our published paper we have shown that the HQ value it should be like 0.25 or 0.5. Then so it should come from the recognized body. So the research should be carried out in this direction, rationalization of safe value of HQ. Then relative efficiency of arsenic uptake by different crops we should measure. Then distribution, obviously distribution in different plant parts, that is important, because if your edible portion or like your edible part is safe, or if it accumulates less in edible portion, then it is safe. Okay, so this is also required. Then development of comprehensive integrated reclamation package for arsenic polluted soil is required. So this is our arsenic research stream. Currently, I'm working with Dr. Achinta Bejbarua in North Dakota State University. All other collaborators are from India. So I'm really grateful to Fulbright Nehru Research Fellowship from United States India Education Foundation, New Delhi, for providing the financial support. Then Indian Council of Agricultural Research, then IARI, Indian Agricultural Research Institute, my parent institute, North Dakota State University, and finally the Stevens Institute of Technology, Hoboken, New Jersey, for inviting me to present here, to come over here. Thank you so much.